Hello developers, let's start developing. Today we're gonna take on the sixth task of the 2024 Advent of Code. Let's see how this goes. Let us read through this. Gart Gallivant, whatever that is. We are going to the year 1518. Yay, great. Yeah, that would be a fun thing for historians to have a time machine. Single guard part of the lab, work out the guard. Okay, we have our maze. We're gonna be running a maze tonight. Making a map. For example, let's see what the puzzle input is. It's a huge map. Do we have a starting position? I think it was like this. Yeah, we're there. So what do we need to do? Current position of the guard. To indicate the guard is facing up, any obstructions are showed as hashes. Strict patrol protocol. If there is something directly in front of you, turn right 90 degrees. Otherwise, take a step forward. Following the above protocol, she reaches an obstacle, a pile of failed suit prototypes. Because there's an obstacle, she turns right. And then again, she turns right, Eventually leaves the mapped area. By predicting the guard's route with specific positions in love will be in the patrol path. So that's what we need to do. We need to simulate the guard. Okay, let's imagine that this is our initial input. Day 6 input, this is the input, and of course we're gonna parse. We need to parse it. How do we do that? Well, we're gonna need to read the matrix. Let's see, do I have... No, I don't have a helper for that. I do actually have some matrix helpers, loop matrix, print matrix. None of them are useful, but let's still model the input. That we're gonna have the maze, which is an array of either a dot, which is a free thing, or a hash, which is an obstacle. We can model it with true and false as well. So basically we can just say that this is a Boolean array of arrays. And we have the start, which is actually gonna be a point that has an X and a Y. We don't have the end because we don't need it. Note that the start is actually a free position. And we will also have to specify that true is open, false is wall. Otherwise, we can model it the other way around and then have some problems. But we have documented what we are actually doing. So now we read the lines, and now we need to map the lines to something. The result, yeah, we'll just need to check that the input is actually of type input. We will return -1 instead of input. And our input will need to be started with, well, yeah, we can do it like this. Now we just need to line off lines. We will need to go through each line, and when we get to each line, we're gonna split it on spaces, and then that gives us a string array. Those are the cells, and we're gonna do something like this. So we're gonna create our row. Now, how do we want to do this in the best way? Yeah, just create the row. That's an empty array. So we're doing row.push false, row.push true. If the cell, and note that we don't need to specifically map the starting position, but we kinda have to for the other thing. So we might get the maze correct, but we don't know where we started. So we will say if the cell is a dot, then push it. Actually, we don't need to do it because we have three options. Dot, hash, caret. So if it's a hash, then we're pushing false. If it's a caret, we're pushing true. But we will need to say which is the start and what is the length. Do we want to do this? Well, yeah. This is a trick because we don't have the index of the row, we don't have the index of the length, but we have gotten how far we got along. So the current length of the maze, how many rows we actually have, is the value of ours. Y of the start position, note that y goes this way, and the x is the current length of the row. And because we just added it, it's gonna have -1, but I will do it this way. So we're not pushing it, we're just taking the current length, and that is our position, because remember, arrays are 0 indexed. So if the length is 5, which means we are on the 6th item, we're processing the 6th item currently, but the 6th item index is 5. Yeah, it's confusing, and off by 1 errors are totally common. So it's this. That's about it. Only the one thing that's missing, we need to add the row to the maze. And we just need to type this as input so that it knows that we're adding a row of booleans. So we're returning the result here. And yeah, let's ignore part 2 for the moment. So now I will actually use the print matrix method that takes something. So we're gonna take the maze, and this actually takes two functions where if we're saying if the item is true, then put a dot, otherwise put a hash, and for the rows index, we don't actually want that. Let's just print our matrix and see what comes along. Yeah, for advent of code, it's often useful to have a method that prints a matrix in a specified way so that we can see whether this thing is what we actually had. The only thing missing is the start position. Yeah, let's add some logic for that as well. So it's not gonna be this, it's gonna be a bit more complicated. We're getting the item, but it seems that my method didn't actually take into account that we might want to use the indexes here. Yeah, I might change it somewhere, but for now we can just literally look the start and the stop and see where we're at. It says that we are X, which is column 4, and 6, that is row 6. Let's see if that is correct. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6. Okay. And by default, we're facing up. So we're gonna need to start moving. Yeah, you know what? I will go here and change this thing. So we're getting our matrix, we're getting our processor, we're getting a row header that we can, but we don't have to do that. But the processor will also get a row index, which is a number, and a column index, which is also a number. So now instead of calling this is the column index, we will call it like this. So now we can do a better print matrix because we can do that. So instead of just the item, we will also get the row and column items. So our code can be a bit more complicated. So if row is the start and column is the start, then we are at the start. So then we return a caret, otherwise return a dot or a hash. Let's see if we print the matrix correctly. Because why am I doing this at this very moment? Yep, we printed the correctly. Because I think that I will want to have the visited nodes in a separate structure, not in the matrix itself. And actually the movement in a separate, but I want to display the matrix with an overlay of the path so that we can get the access. So it's a good thing that this works. Still, I will turn it off. So I will add a visited things that will be a set of number pairs technically, but comparing number pairs is a bit of a pain in the ass, so we might want to have a string. Yeah, we can put data here in the format, for example, 1, 1, which means that, or row 1, column 1, or row 1, column 3, or something like that, to avoid the issue, because strings are easy to compare inside the set. Arrays are not so easy, which means that I will actually want to have two helper methods and a type. We can do all of this inline, but it's much easier for my mind to actually have this. We will have a type that's called point that has x that is a number and y that is a number, maybe not point, maybe position. It's kind of the same, and now we can say that the start is a position. So I will have toString, which takes a position. Actually, we can even deconstruct this immediately. We have an x and a y that are coming from a position, and what we are returning is, that's good enough. We can use a comma, but to be honest, I usually prefer a colon as well. And of course, we're gonna have to have a from string, which takes a string and returns a point. So st, we're gonna take that string, we're gonna split it, we're gonna map it through a number. Actually, we can be fancy with TypeScript. It doesn't take a string, but it takes a number, comma, and then another number. And we can even give it a name. No, let's leave it like this. So this is a weird TypeScript type. You don't have to use it always, but we can also say it's a string. Not the value. I don't like the number constructor, but I like the parsing better. Those are the values, and then we return values of 1 and values of 0. So this is a way to get from a position to a string and from a string to a position transparently, more or less. So we're gonna say, and the original visited, do we need a cube? Not really. But I can say that visited.add at the start as a string to the visited. We're gonna need to have a direction, which is gonna be basically position, which is the start position, and a direction that is up. Let's have yet another type, because for me it's kind of okay when I visualize where things are going. It's quite easy to, when I have it typed correctly, it's quite trivial sometimes to say what you actually want to do. And oftentimes, if you specify the thing correctly, you will get to a point when the specification is trivial to write in the correct typing. So it's not a direction, it's just, the direction by itself will be basically just up or down or left or right. That's the looking, the thing, but the guard position, we can also call it guard position. Or we can actually call it the state, because the state, that's the state of the guard. He has a position and he has a direction, so we can say that this is the state, which is of type state. Okay. And we don't really care about that, we just need to move. How long we are moving? Where we're moving all the time. So let's move that. So how does the guard make a step? I think it will be easier to have a while true loop, and then we're gonna break inside the loop. So the new position of the guard depends on whether the thing in front of him is a wall or not. And oh, and we can now abuse a bit our types, so that we can have another method that will say, will basically be move in a given position, in a given direction. So we're not gonna do that. We're just gonna have a state. So we have the position and the direction, which is actually a part of the state. And how we change the state if everything is okay. So we're just gonna return a state. Yeah, something along these lines. We're gonna need to have a case. So we don't even need all of these thingamajigs. We're just gonna have the switch. It's kind of too wordy. So if we're moving up, that means that we need to return this thing as the state. Do we want it to give it the state, or do we want to give it the position and direction? Yeah, okay, it's okay. We're just gonna return our position because the state doesn't actually change. So we don't need the breaks. We're just returning the changed position. This is one thing that always annoys me, that when we have matrices and moving through dimensions, we have the same code 4 or 8 or 12 times or something like that. But this method we have to have that because it is different. But this method will help me encapsulate that. And I will add another method that I will call turn, not turn left, which also, no, we have, oh, it's actually turn right all the time, right? Turn right, which also has a position and a direction. But note that when we're turning now, we will have to just turn, because what happens if we have, let's say, a situation like, yeah, imagine this is the grid. If we have our guard here and we have a thing like this. So the guard goes here, then goes here, then goes here. Then if we say turn right and take a step, that will take the guard here. That's not something that we want. We want the guard to turn in this direction and then check again, and that will mean that the guard will turn in this direction, so he will then continue moving this way. Yeah, he will just go back where he started. So we need to make sure that we don't actually run into a wall. That is quite common with processing mazes. So when we're turning, in this case, we changed only the position and we returned the position. So when we're turning, we're just only gonna change our direction. So yeah, this is right. We don't really need the position. We can have it as a discard parameter. And yeah, we're gonna give it a state, but we're only gonna use direction. So if it's going up and it turns to the right, it goes right, down becomes left, left becomes up, right becomes down. Yep. Up becomes right, right becomes down, down becomes left, left becomes up. I will reorder this so that they kind of run in a circle. Up becomes right, right becomes down, down becomes left, left becomes up. Okay, we have those two methods. We have the switches out of the way, so we don't have uh, anything. So where is the next move? Where will the next move take us? And now we need to check, is the next move a wall? Is the next move available? Now this we said, true is open, false is wall. Is the next step available? If it is, then we are changing the position and adding that to our list of visited items. The way we build it with a set, sets have basically only uh, are sets, mathematical sets. If we put in 3, the value 3 times in a number, in a set of numbers, we will just have it. We cannot say how many times we have it. That doesn't make sense for a set. Set can have something, or a set can have don't have something. Those are the only two options. Anyway, if that is a wall, then we're turning right. And that's all there is. We will just need to add another check. If we go overboard. So I will actually have this somewhere. I think it's good to have it. Have the width and the height, and now I think that this will generate a bit better code. So if we go out of scope, we're just breaking. And that's all there is. We've simulated our guard. We can have him move, have him express an intention of moving. If he moves into a, yeah, if he goes overboard, we're done. If he moves into a wall, if it's available, we're gonna move there. If he moves into a wall, we're just gonna turn him. And loop, and loop, and loop, and loop. So now we're just gonna say return the size of the visited, because that's what we want to do. So in this position, it should go through 41 items. I would be relatively surprised if this returns 41, but on the other hand, it's quite possible. And it did. So I'm not gonna second guess myself now. I will just try to give it the huge input and have the guard walk through the maze. Let's see if this works. And note that anytime that you have a while true loop, it might take a while, or it might never finish if you have an error that you made an endless loop. It says it's gonna visit about 5,000 places. Let's see if that is the correct number of places. Yep, our 11th gold star. Now let's get to the complicated part, because I expect this one to be much worse. Fancy device, time travel to the last few months and record the nightly status of the lab guard post. Okay. A single new obstruction. Oh. All of the position. New abstraction. Well, I'm quite sure that there are two different ways to solve this. What is the task? Now, we have this, and we want to have the guard stuck into a loop. For example, the guard goes up, hits an obstacle, the guard goes this way, hits an obstacle, the guard goes this way, hits an obstacle, this way, then this way. But what would happen if we had a hash here? The guard goes up, tuck, 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 tuck. So the guard is stuck in an endless loop. The obstacles are added in exactly such a way that they make the perfect loop. But note that the loop is not the one way that we can see this loop is basically to have a rectangle, because these four, if we consider, they are always, if we have a rectangle, they are always one off. So we have a situation something like this. If this is the rectangle that we want to do, and when I find where to place the borders, where were the borders? Borders. Never mind. Imagine that we have borders on this part. If we have something here, and here, and here, and here. So you can see how they relate to this rectangle here. So if we have that such a case, and the guard gets into that rectangle, he will stay here. She will stay here. So that is, oh, these are the borders. Yeah, it looks much better now. So the guard will stay if he gets to this, any of these fields, moving in the good direction. She will just keep looking over and over and over and over again. So now I can think of two ways to solve this, to basically do an analysis. But an analysis is a bit hard to do, because see what this path is. If we have, if we put a wall here, then the path goes like this. So it's a complicated path. It's not a single rectangle, but it's multiple rectangles together. In this case, for example, when the guard gets here, he's trapped into a rectangle and he has that. Or in this basic case, but in this case, he's trapped into something that's actually a figure eight or something like that. Or I guess this is even an even worse situation. He's trapped in a what? I don't see it. He goes this way, boing, boing, boing. He's going this way, then this way, then this way, then this way, then here, then here, then here. Oh, he eventually gets trapped in this rectangle. Yeah, this is the rectangle that they get trapped into. Yeah, so this one is actually simple, but this one is complicated because the route that they get trapped into, it's not a rectangle, it's a complicated, and we don't have a specific. If we had a stop here, it would have been a rectangle, but it's not. So that's the logic of it, and whatever we do, we can say that this is getting complicated. My other idea, however, is to do it brute force. What can we do? We can actually put in a obstruction anywhere and have the guard go through it. And we'll see if sorry, it's a female guard, I keep making the mistake. If they get to a point when they are in the same position with the same direction, so if they repeat a state, they are in a loop. That's the issue. because they can repeat a position, but if they repeat a position going in a different direction, that's quite okay. But if they repeat a position going in the same direction, they are stuck in the loop. Basically, if they repeat a state, they are stuck in a loop. And we have basically a few thousand items. Let's see how many. In order to brute force something, we need to know how much force will be needed. So this is 130 by 130, which means that we have an option of putting an obstacle in this many positions. Note that this grows quite fast. If we had 3 dimensions, it was 130 by 130 by 130. This might be a bit difficult because this is kind of 2 million times. But if we have no third dimension, basically we will need to run our solution for 17,000 times. Let's try that. I will try that. And why I like doing things like this. They might seem silly, but the best case scenario, brute force will work and I will get the answer in a very, very reasonable amount of time. But if brute force doesn't work, what will happen? We will have some insight of what is happening and how it's happening, and we will spend some time thinking about the problem, and maybe we will get a better feel of how to solve it properly. So, and I kind of like it that it's easy to think of a brute force solution, basically check everything, and it's easy to start doing something. And if in the middle of that I say, oh, I have a better idea, I will go to that. That's not a problem. But I know that the brute force solution is a trivial solution to the issue that I have. So let's try it. We will need to copy a lot of the first thing because now we have a state. We will need to have a method to copy matrix. Don't we have that? So we want to have our thing with an added obstacle. So let's take in the height and the length because those are going to be useful anyway. And no, this is not an element, this is a row. Oh, not height, dot length, only height. And this is the index of the row. And there we're gonna also loop through the cells and we will have our cell. If that cell is already a wall, we cannot add an obstacle over there. So if it's, once again, true is open, false is wall. So if this is false, we cannot do anything. We don't need to do anything that is already a obstacle. Otherwise, make a copy of the maze with the added obstacle. So change all the rows, and row.slice will work since we only have booleans. We don't have complicated things. And then we are setting that specific cell which we have, which is index, to false. And then we need to do part 1, basically, with this thing. So I will extract that to a specific method. Is it looping? I will call it will it loop. So we're gonna take some. No, we're not gonna take an input. We don't really need an input, do we? We need a maze. And we need a state, which will indeed have a position and direction. So that might have been great. So this will do something that will tell us whether the guard will loop or not. So now it's quite simple. We're just gonna need to call this is the number of positions where it will loop. So now we have our changed maze. We just need to say will it loop with that maze and then put in the position, which is the input dot start, and with an up direction. Will it loop? We have no idea. But now that I look at it, I think the previous signature was better. So yeah, we technically have a state, but it's kind of broken in two. So we have only this. This looks a bit nicer. So if this thing loops, we just need to say positions, add 1 to the number of positions where putting an obstacle will cause the guard to loop. And we're done. We just need to return the number of positions. Do we have the small number? Yeah, we need the small input. Actually, I'm gonna copy it over again since I think I was playing around with it a lot. Yeah, that's better. And we have just one thing left to do, one very simple thing to do to determine whether this will loop. Well, that is something like this. We're gonna need to loop through that, but we will need to define our initial state. We're gonna need to have. Okay, the construction noise has stopped for a while, so we can continue. So, in order to determine whether something will loop, we'll have the guard go through it, and if the same state happens again, then we will just break, because that's done. So we will need to define the initial state. That's the position and the direction. So we're gonna move to the next. Of course, we're gonna need the width and the height. We don't have the input part here, we just have the maze. So if it goes out of the maze, then it's easy. We're just gonna return false because the guard doesn't loop. If he exits the maze, he is gone. Otherwise, add it to the visited ones and turn right. But now we will also have yet another check here. Is the current state already in the visited path? So now, instead of doing this to string, I will create yet another method. So this I will rename the original. We ended up not using this one. But we'll have this position to string, because what I want to add now, we'll have to call it state to string, which takes a state and returns something like this. It actually wanted to call the previous one. I think it's might be even better to do something like double deconstruction. Oh, let's just leave it. It will have to be a lot of specific syntax. So we just say position the text, comma. So whatever it is, from a unique state, we are generating a unique string. And now we will just say state to string of state. And of course, we will use this here. Not next, but state. No, before we need to have to check it before we make a step. We need to check it here. Yep. So when we're about to take the next step, we check whether we were already there. And we were already there. Yes, we rendered a loop. And return true or return false. Otherwise, continue moving on and on and on and on. I have no idea whether this will go into an endless loop or not, but there's kind of one way to find out. So it says we have 6 places when we can position some things that will actually stop the guard from moving. Do we have some locations? Do we need to put them in? But we got the correct value. So let's try this on the big input. Let's grab it and have it run something like 17,000 times. A bit less because it won't run for the actual obstacles, but not too much. I think it should take a few seconds at most, but we can have a situation when we have to grab a coffee or do something like that. And after only 45 seconds, we got our result. It's 1434. I hope this is correct. If it's not, then we're back to square one. Let's check it. Yes, that is the right answer. And by checking all the possible obstacles in all the possible ways, we kinda made some things. One thing that immediately kinda pops to mind is that in the task, if we look at this map of axes, we can kinda obviously see which positions are irrelevant. So it doesn't really matter if we put in an obstacle here, or here, or here, or here, or kinda in any of these, because we never have a situation when the actual guard is wanting to go that way. So in none of it makes sense if we put an obstacle only in the positions where we actually have an X, because that will change the path that the guard has. So that will be one optimization that we might want to do. And in this case, unlike in task 5, in task 5 we also had a huge slowdown, but the slowdown was kind of second or more. So we might not optimize this if it's good enough. Most likely, I already have a lot of ideas how to optimize it because I kind of hate the solution since it's way too brute forcing. On the other hand, the solution for the 6th is way too slow. If we run all the tasks, it will take most of the time just to solve this. So I think there will be yet another video on this task when we will try to optimize it and make it better and faster. Anyway, if you like this solution, even if it was a bit brute forcey, don't forget to mash the buttons, click like, subscribe, definitely comment if you have something to say, even if it is to say that this is the best video ever or the worst video ever, and keep developing.